Hello, Internet. This is JF, and I suck at ATS. What you're looking at is a benchmark on the left in ATS and on the right in C. It's a benchmark because it's a really silly it's a silly task. Like I'm just counting up like the number of ways you can use change to add up to like $10. So let's see this using this array of like pennies, nickels, dimes, quarters, and you're just like okay, how many ways can I get 10,000 out of these? So you can have like 10,000 pennies. That's one way. That sort of thing. I think that's what it is anyway. But it's this is a program that benefits enormously from memorization. So if I compile and run these, it'll take like hundreds of milliseconds. But with memorization, they're basically instantaneously. And although there's a lot of performance variation in the way they're implemented right now, with memorization, it's instantaneous no matter what the language is, pretty much. So I've got some fourth implementations of these that take like seconds. I've got a Haskell implementation that takes like 6 seconds. But yeah, they improve enormously if you just stop recursing so much, which is what they do twice each run. So if you look over here, you have a CC function. It takes an amount and it takes an offset into this array. That it returns 0 or 1 in some cases, and then the default case that it recurs on itself twice and adds up the result of the two recursions. And that's the same thing that the ATS is doing. So I could take the smaller and the same. What is that? The smaller index or the same index. So that's what the smaller or the same is from. Let's add this up. And this ATS is very similar. It takes the sum, the amount we're going for. It has an OOP index, an out of bounds index, which is it's an OOP index of n. So and I also have coins of n. So this is an array of ints. It's an array, in fact, of 5 ints. So this is an OOP index of 5, which means that this index can be anything from 0 to 5. But also -1. So that's what I'm saying, like OOB for out of bounds. It can be from 0 to 4, So it can be a proper index, or it can be -1. That's the options in that one type. -1 is a valid thing. Yeah, see, if I is less than 0, then 0. That's one of the options for it. It's one of the cases. And I'm using an if case here instead of like a case structure, which is a nice way to have multiple ifs. So these are all just if I equals less than 0, if sum is less than 0, if sum equals 0. It's pretty nice looking code, I think, except for the usual problem of it being really long. And this is after I've sort of used type defs to pull stuff out and give them names and such. All right, so I've got these are the two. Yeah, this is ATS and C. So let's go ahead and run them. I've got a little make file here that runs them for me. So ATS, about 350 milliseconds, 340 milliseconds. We don't need to be exact because the differences are fairly large. This is the same program in ML. Go ahead and pull that one up. Coin.ml. Yeah, same exact thing. So there's the sum and the index, and it uses the index into the coins. This is like identical to the ATS code, pretty much. Which has 850 milliseconds. All right, then we have coin C. This is the C code we're looking at. So this is like 550 milliseconds. So it's slower than the ATS code. And then we have ATS coin, which is this is a little bit different. So I'll get to that in a moment. But the point is, or the first point is, hey, look at this. 300. You're seeing 300s here. It's consistently 300s, and then you can go past ML, which is slower. And they get back to C again, and C is 500s. And they are the same exact algorithm, written like the same exact way. Like I'm not using any tricks. Like it's just ATS. Like if I were to take the C and say, how do I write this in ATS? I would do that. And in fact, the person who wrote the C wrote it by copying my ATS. So it's like it's the same algorithm. But yeah, the ATS is much faster. And then ATS coin. The second one. The second one is from this file. Let's see, what's it? No, it's coin-c. No. What DATS files do I have here? What C files do I have here? Okay, ATS coin, not C. That follows. So this looks a little bit weird. I have some type defs here. I'm just saying, okay, ATS type int, it's an int. A bool is also an int. A pointer, it's an int to a pointer, whatever. These are type defs that I made just to make the following code work. And the following code is what ATS actually generates. Because obviously ATS, it doesn't necessarily have to generate C, but here I am generating C. I'm compiling C. So it's weird for the same algorithm in ATS and in C for there to be a speed difference. Well, this is the kind of C that ATS generates. So it generates a bunch of temporaries. And you have that if case. So, if the index is less than 0, if the sum is less than 0, if it's equal, it does all that stuff. And actually, this isn't exactly what ATS generates. What ATS normally generates, we can go look at that. What do I have? Let's remove, what is it called again? Okay, coin ATS. So remove coin ATS and make it, yeah, that's how I'm making it. So let's run the same thing. So here's log C 30 coin ATS. Actually, no, don't do that. Do coin.dats with dash capital E. So this will give us the generated C code. And then that's not really pretty, so let's go ahead and remove remove empty lines. Remove lines that are comments, and also lines that are just empty. They don't have anything. They're consist entirely of white space. Then run indent over that, and then do a less on that. Indent doesn't like that. Okay, it worked. It worked. So what's this function called? It'll be called count. What on earth? All right, count. There's a struct for it. Okay. I'm not indented any. Okay, yeah, this is the function. It doesn't look as nice because indent was flaking out for some reason. We can see this is what it actually generates. And what it generates, it has these long functions like, ATS prelude less than, G1 int 11. This is less than sign. This one, this is also a less than sign. And this one, this is an equal. I'm saying arg0 equals 0. That's all it is. And these are actually in the output as well. Int 9 1, and if you find it, yeah. So there's a bool, and it just does a comparison and returns a bool, but it's inline, so it just gets inline. So what I'm doing here is I'm just removing all these functions that are all inline, and I'm putting in the actual code. So a less than sign instead of a function, an equal sign. And you can see that doesn't change it because let's look at the times again. So 300s for ATS, normal ATS, and then 500s for C, and then 300s for the C code right here that I have where I took all the inlines out and I'm just putting normal stuff. So it doesn't make it any faster or slower to do it that way. It's the same thing. So you can see that this is the C code that we get from ATS, and it compiles to something that's really faster than the naturally written C. So I think that's interesting. Like normal C compilers are not as good at optimizing naturally written C as they are optimizing this thing with all these temporaries that are only used once. That are somebody looked at this code and they said, well, that looks like exactly what the C compiler should do with the original C, but somehow it doesn't do it. Somehow ATS doing this makes it better. Right. And that's pretty much all I wanted to show you, except for the that PATS capital E thing, which you can do to look at code. I can also look at assembler for the same way. All right, that's it for the video. Short video.